Welcome to the 7th lecture of the NPTEL MOOC on parallel algorithms. In the previous couple of lectures, we have been seeing various algorithm design techniques. Today, we shall discuss an algorithm design technique that we shall call accelerated crowding. In this design technique, we have a problem instance, the size of which shrinks through steps, but the number of processes remain the same. So, as the problem proceeds through the steps, as the algorithm proceeds through its steps, we find that the same number of processes are crowding over smaller and smaller problem instances, and therefore these smaller problem instances can be solved faster. A crucial notion here is what is called the processor advantage. The processor advantage of an algorithmic instance is the ratio of the number of processes available to the problem size. Let us say we have an input of size n. And we try to solve this input of size n using p processors. In that case, we say that the processor advantage is p by n. You have p processors to solve an instance of size n, therefore the processor advantage is the ratio p by n, the number of processes available to the problem size. In the algorithm design technique that we call accelerated crowding, suppose for a problem p we have a super fast algorithm, but let us say this algorithm is rather wasteful in processors. Let us say we want to design a moderately fast but economic in processors algorithm. A solution can be found usually by iteratively reducing the problem size so that the processor advantage of the new instances increases exponentially through the iterations. We will consider an example. Let us say we want to find the minimum of n elements. For example, given an array of size let us say 4, we want to find the minimum of the array, which is in this case 1. So, we assume we are given an array of size n, but let us assume that we have n squared processors. For a problem size of n. So, in this case n squared equal to 16, we have 16 processors, let us say. Using these 16 processors, what we do is this: we take a 2-dimensional array, a 4 by 4 array, along the columns we have, along the rows we have these values 4, 3, 1, 2, and along the columns also we have these values 4, 3, 1, 2. At each cell of the 2-dimensional array, we compare the row value with the column value. If the row value is greater than the column value, then we write a 1 in the cell, otherwise we write a 0 in the cell. At the diagonal positions, we will have zeros, because when 4 is compared with 4, we have equality, not a greater than sign. So, at all the diagonal positions, we have a 0. For a row value of 3 and a column value of 4, we have a result of 0, because a 1 will happen only when the row value is greater than the column value. For the same reason, the value here will be 1. For a 1, 4, we have 0. For a 4, 1, we have a 1. For a 2, 4, we have a 0. For a 4, 2, we have a 1. For a 3, 1, we have a 1, but for 1, 3, we have a 0. For 3, 2, we have a 1, but for 2, 3, we have a 0. For 2, 1, we have a 1, but for 1, 2, we have a 0. So, the array is filled in this fashion. For each location of the array, for every ordered pair ij, the array location will be filled if the row value happens to be greater than the column value, then the array location will get a 1, otherwise it will get a 0. So, when the array is filled in this fashion, let us say for each of the rows we take the minimum, we take the OR of the bits in that row. So, in the topmost row we have 0, 1, 1, 1. So, the OR of these 4 bits is 1. In the second row we have 0, 0, 1, 1, again the OR is 1. In the third row we have 0, 0, 0, 0, the OR of these 4 is 1, it is 0. In the bottommost row, once again we have 1. So, we find that a 0 happens exactly for the smallest element in the array, because this is the element which will be adjudged less than or equal to every single column value, including itself. Therefore, for this particular element, every single entry in the row is going to be 0, and this will be the only row for which the OR value will be 0. So, when we look at the OR results, the value for which the answer is 0 will be the smallest element in the array. So, the algorithm that we have just seen works like this. We are given an array of size n. We want to find the minimum of this array. First, what we do is this: we take a 2-dimensional array, and then for each location ij, we fill the location with the Boolean value ai greater than aj. That is, if ai is greater than aj, the location will get 1, otherwise the location will get 0. So, this is what we have done here. In the 2-dimensional array, we have filled the logical values after every comparison. Since we are doing this in parallel for every ordered pair ij, we will require n squared processors, because the 2-dimensional array, which is an n by n array, has n squared locations, and for each location we will have to dedicate a processor. With n squared processors, since what we have is a common CRC-WPRAM, concurrent reads are permitted, therefore multiple processors can read the same input value simultaneously. That is, ai can be read by several processors simultaneously for each I, and therefore bij can be filled in order 1 time. So, the array is filled in order 1 time. Then in the second step, we have several parallel executions, one parallel execution for each row. What we do is to invoke the OR algorithm for common CRC-WPRAM that we have studied in the earlier lectures on each row independently and in parallel. The result of the OR will be kept in Ci. That is, for the result of row I will be kept in Ci. If Ci happens to be 0, we know that exactly one row will have a 0 value. If the minimum is unique, then the corresponding row value ai will be returned as the smallest element. What if there are multiple minima? Then corresponding to all those elements we will have a 0 value, and all of them will be attempting to return the corresponding row values. But all these row values are identical. Therefore, on a common CRC-WPRAM we will have a concurrent write, where every processor attempting to write will be writing the same value, which is a valid write. Therefore, the write will go through. The algorithm works correctly. So, we find that there are only 3 steps. Each of the steps of the algorithm will work in unit time. So, we have an order 1 time, we have now order 1 time algorithm using n squared processors. To solve an instance of size n. Therefore, the processor advantages n squared by n, the number of processors divided by the problem size, which is n. So, here we find that the problem size as well as the processor advantage are identical, which is n. So, what we know now is that the problem of finding the minimum of n elements can be solved in order 1 time on common CRC-WPRAM using a processor advantage which is equal to the problem size. Please take a look at the algorithm specification here. The processor allocation has not been made explicit here. In the first step, all I say is that for all possible ordered pairs ij, bij has to be filled according to the specification. But then which processor should do the copying of which ij is not specified. So, that allocation is unspecified here. So, hereafter in algorithm descriptions the Padu variable will not always represent processor indices, but will still be indicative of the parallelism. The allocation will not always be explicitly stated, but in each case you would be able to figure out the processor allocation easily enough. So, this algorithm runs in order 1 time with n squared processors. This is a super fast algorithm, but it is very wasteful in processors. It is a non-optimal algorithm. To find the minimum of n integers, all you require is order n times sequentially. Therefore, we would expect an algorithm to run in order n cost, but this is very wasteful. This algorithm runs in order 1 time using n squared processors. Therefore, the cost of the algorithm is order of n squared. Now, suppose we want to design an algorithm that uses NR processors, where R is less than n. That is, the initial processor advantage is R instead of n that we have just seen. So, what we do is this: we divide the given array into a number of segments. Each segment is of size R. So, the segments can be numbered like this. The leftmost segment is called the first segment and the rightmost segment is called the n by rth segment. To each segment we allocate R squared processors. So, the total number of processors allocated is R squared is the number of processors allocated per segment and n by r is the number of segments. So, the product is nr, which is indeed the number of processors that we have. And the number of elements in all the segments put together is r into n by r, which is n. So, as you can see, the processor advantages are initially, and the problem has been divided in this fashion. Now, each of the segments can be solved in order 1 time because the segment has a size of r and there are r squared processors allocated to the segment. Using the algorithm that we have just seen, where the processor advantage is equal to the size of the problem can be solved in order 1 time. So, each of these segments can be solved in order 1 time. That means we find the minimum within each segment. How will we find the global minimum now? We have obtained the local minima of the segments. If you take the minimum of all these minima, then you would get the global minimum. Let me take an example. Let us say we have an array of size 12, A and B are hexadecimal, 10 and 11 respectively. So, let us say this is the given array. Suppose we divide this array into segments of size 3 each. Our goal is to find the minimum in the entire array. We divide this into several local problems and solve each local problem. The smallest element within the first segment, which is 5, 8 and 2, is 2. The smallest element in the second segment, which contains 4, 9 and 3, is 3. The smallest element in the third segment, which contains 1, A and B, is 1. And the smallest element in the fourth segment is 0. So, the original instance of size 12 has now reduced to an instance of size 4. If you find the smallest of these 4 elements, you would have the answer for the global problem. The smallest element in the array in any case would have been a local minimum as well. Therefore, when we find the local minima, this certainly would be selected. Therefore, in the reduced problem instance, the smallest element will be present. And this indeed is the global minimum, therefore, it will be smaller than any other selected elements selected from the other segments. Therefore, when we take the minimum of these elements, you will indeed be returning the global minimum as the value. Therefore, the idea of our algorithm is correct. So, now let us see how the algorithm proceeds. If n equal to r, that is the processor advantage is identical to the size of the problem, we invoke the previous algorithm which runs in order one time. Otherwise, we divide the array into r segments, the segments of size r. So, there are n by r segments. For each segment in parallel, we invoke the previous algorithm using r squared processors. Then we invoke minimum 2 recursively using this reduced array. The new array is given in B and it has n by r elements. On these n by r elements, we would invoke min2 recursively using a processor advantage of r squared. Why is the processor advantage r squared now? Initially, we had a problem size of n, the number of processes nr, which means the processor advantage is r. Now, after one invocation, the new problem instance has a size of n by r. That is because we have one element coming out of every single segment and there are n by r segments. So, the new problem size is n by r. The number of processors is the same, we still have nr processors. Therefore, the processor advantage is nr divided by n by r, the number of processors divided by the new problem size, which is r squared. That is, the new problem size is n by r and the new processor advantage is r squared. This allows us to write a recurrence relation T of nr, that is when we invoke the algorithm with a problem size of n and a processor advantage of r, we find that after spending order one time, we managed to reduce the problem size to n by r and increase the processor advantage to r squared. Therefore, the recurrence relation will be like this. If we continue with this now, the new problem instance is n by r and the processor advantage is r squared. Therefore, now we will be dividing the array, the remnant array of size n by r into segments of size r squared each. Therefore, we will have n by r divided by r squared, which is n by r cubed, these many segments, and we will have one element coming out of each segment. So, the new problem size will be n by r cubed and the number of processors remain identical. Therefore, the processor advantage will be nr divided by n by r cubed, which is r power 4. Therefore, the recurrence relation that we have is this: T of nr is T of n by r, r squared plus c. So, when we unroll this once more, what we get is, now the new problem instance is n by r cubed and there are nr processors still for a processor advantage of r power 4. Therefore, at the next level of recursion, we would be dividing the remnant array into segments of size r power 4. So, there will be n by r power 7 segments now. Therefore, the next iteration will have a problem instance of size n by r power 7 and therefore, the processor advantage would be r power 8. So, if you continue like this, now the pattern is clear. If you continue like this for s steps, you would have 1, 3 and 7 are all 1 less than a power of 2. So, you can write this as 2 power s minus 1. The processor advantage now would be r power 2 power s. This will be the situation after S levels of recursion, and you would have spent a total of SC time until then. When would the recursion stop? The recursion stops when the problem size is equal to the processor advantage. That is because when the problem size is equal to the processor advantage, we can invoke the first minimum algorithm that we saw that runs in order of 1 time. So, after S steps, if we were to invoke that algorithm, that would mean the number of elements is equal to the processor advantage, which means this implies that n is equal to r power 2 power s into r power 2 power s minus 1 or r power 2 power s plus 1 minus 1. N is equal to this. If you take logarithm on both sides, logarithm to the base of r, you would get 2 power s plus 1 minus 1 on the right hand side, which means log of n to the base r plus 1 is the same as 2 power s plus 1. If you take logarithm once again, you have logarithm to the base 2 of log n to the base r plus 1 is equal to s plus 1. That tells you after how many steps the recursion would stop. That is, s is equal to logarithm to the base 2 of logarithm to the base r of n plus 1 the whole minus 1, or which is order of log 2 of log r of n. So, the algorithm would run in order of logarithm to the base 2 of logarithm to the base r of n using NR processors. So, let us see what this entails for different values of r. If you take r as n power epsilon, that is the number of processes P is NR, which is n power 1 plus epsilon for a small constant epsilon. We find that log r is epsilon log n, that is log n by log r, which is the same as log n to the base r, is 1 by epsilon. Therefore, the running time of the algorithm would be, which is order of log to the base 2 of log n to the base r. This would be the logarithm of 1 by epsilon, which is order of 1. So, the algorithm would run in order 1 time using n power 1 plus epsilon processors on the same model. So, this is an improvement. The first algorithm that we had ran in order 1 time using n squared processors. This new algorithm also runs in order 1 time, but uses n power 1 plus epsilon processors. The only difference is that the constant factor involved is larger here, because here the actual running time is order of 1 by epsilon, log of 1 by epsilon. The smaller epsilon is, the larger 1 by epsilon is. Therefore, log of 1 by epsilon is an increasing function in epsilon, in 1 by epsilon. Therefore, the constant factor here is larger than the constant factor in the earlier algorithm that we saw, but the number of processors used is substantially less. From n squared, we have reduced the number of processors to n power 1 plus epsilon. That is if you have r equal to n power epsilon. Let us try another value of r. If n is equal to 2, then the running time is order of log to the base 2 of n, and the number of processors is to n. That is, if the processor advantage is 2, then the number of processors is 2n and the running time is log of log n. Log of log n is an extremely slow growing function. It is a logarithm of the logarithm. Therefore, even for a number of the size of 2 power 65536, log of this would be log of 65536, which is 16. Therefore, for all practical values of n, you could say log of log n is less than or equal to 16. So, this algorithm is indeed very fast. If you have an algorithm that runs in order of log n time using 2n processors, then since the model is self-simulating, we can simulate the same algorithm using n processors for the same time complexity. You have the number of processors, the running time doubles, but even with a doubling of the running time, we still have order of log n running time, and we have now used n processors. The algorithm is still not optimal. The cost of the algorithm is order of n times log of log n, whereas finding the minimum of n elements sequentially takes only order n cost. Therefore, the algorithm is still not optimal. This is a suboptimal algorithm, but it is a very fast algorithm indeed. It runs in order of log n time. So, to summarize, the algorithm for a constant epsilon, where epsilon is between 0 and 1, runs in order of 1 time with n power 1 plus epsilon processors. Instead, if we let r equal to 2, then the running time of the algorithm is order of double log n. That is, the minimum of n numbers can be found in order of double log n time with n processors. This is an example of the algorithm design technique called accelerated crowding. The next algorithm design technique that we are going to study is one that is familiar to you from the sequential algorithm setting. It is called divide and conquer. So, in this case, a given instance of the problem is divided into multiple problem instances of smaller size. We solve each of the smaller instances independently and then combine the results to form a solution for the global instance. We would consider a familiar problem, for example that of prefix sums. What we do is this: suppose we are given an array of size n, of which we want to find the prefix sum. Let us say we divide the array into two halves. We solve the prefix sum in each half independently. Then the rightmost element in the left instance, this will be the sum of all the values in the left half. But when the right side of the division was solved, the elements to the left weren't considered. The prefix sums were computed starting from the point of division. To get the correct prefix sums in the right half, what is needed is to add the sum on the left side to every single element on the right side, which means this sum value must be added to every single element on the right side. So, this is the recursive algorithm for finding prefix sums. Let us work out an example. We are given an array of size 8. This is the same example that we saw before. We divide this in the middle. So, we have now two problem instances of size 4 each. To solve the left instance, which is 4815, we again divide this into two problem instances of size 2 each. To solve this instance of size 2, we again divide it into two instances of size 1 each. The solution of an instance of size 1 is clear enough. The values are identical to the given values. When we have an instance of size 1, the problem has a trivial solution. Then the rightmost value of the left solution, which in this case happens to be 4, this is to be added to every value on the right. The left value will remain as it is, but the value on the right will have to get this 4 added to it. Therefore, the right value will now be 12. So, the solution for the array of size 2, namely 4 8 is 4 12. Now, let us consider the instance 1 5. This is divided into instances of size 1 each. Their solutions would be 1 and 5. You take the solution of the sum of the left side, which is the last value on the left side, which in this case happens to be 1. This 1 has to be added to every value on the right. There is only one value on the right, which is 5. So, 5 plus 1 is 6. On the left side, we have 1. So, the solution for the instance 1 5 is 1 6. Then, combining the solutions 4 12 and 1 6, we take the rightmost sum on the left side, which is 12, and this 12 is added to every value on the right side. Therefore, we have 13 and 18 here, and on the left side we have 4 and 12 remaining as it is. So, the instance 4815 has the solution 4 12 13 and 18. As you can see, the solution is correct. Similarly, for the instance 2736, we form the solution 2 9 12 18. So, now the problem on the left side as well as the problem on the right side have been independently solved. To find the global solution, once again we look at the rightmost sum on the left side, which in this case happens to be 18, and add this to every value on the right side. Therefore, the final answer would be, on the left side the values are written as it is. So, 4 12 13 and 18, and on the right side we have 18 added to these values, 18 plus 2 20, 18 plus 9 27, 18 plus 12 30, and 18 plus 18 36. So, the final prefix values are prefix sum values are 4 12 13 18 20 27 30 and 36, which you can see are correct. So, in general, the algorithm proceeds in this fashion. Given an array of size n, where we assume that n is a power of 2, the algorithm proceeds like this. If n equal to 1, return the array as it is. That is, if the input is an array of size 1, nothing is to be done. The array is returned as it is. Otherwise, for I varying from 0 to 1, that is, there are two instances, I equal to 0 and I equal to 1. These two instances are to be executed in parallel. Padu for 0 less than or equal to I less than or equal to 1, two instances to be executed in parallel. We solve two instances. When I equal to 0, we are invoking prefix sums 2 recursively on a 1 to a n by 2. When I equal to 1, we are invoking the algorithm recursively on values a n by 2 plus 1 to n. So, the two halves are solved independently and in parallel. The corresponding results are stored in the B array. And then for every element on the right side, there are n by 2 elements on the right side. So, for I varying from 1 to n by 2, we do this in parallel. The content of n by 2 plus I will be enhanced by the content of Bn by 2. Bn by 2 is the leftmost element, rightmost element on the left side. This is added to every single element on the right side, and then the array B is returned. So, this is the recursive specification of prefix sums 2. So, let us see what is the time complexity of the algorithm. We find that the time complexity is like this. When we are given an instance of size n, we form two instances of size n by 2 each and solve these two instances independently and in parallel. And then combining the results, we spend another order 1 time. We take the leftmost element, rightmost element on the left side and add this to every single element on the right side. If we use a CR EWP then this value can be read by every single processor on the right side simultaneously, and the addition will take only order 1 time. Therefore, C1 here is a constant. So, the recurrence relation is T of n equals T of n by 2 plus C1. You can see that the solution for this recurrence relation is order log n. That is because T of n is T of n by 2 plus C1. If you unroll this recurrence, we find that this is T of n by 4 plus C1, which is 2C1. If we unroll once again, we have T of n by 8 plus 3C1. So, in general, if you unroll k times, we have T of n by 2 power k plus kC1. If you put k equal to log n in particular, this becomes T of 1 plus C1 log n. But when there is only one element in the array is returned as it is without doing anything. So, the algorithm would take order 1 time. Therefore, this is order of log n. That is why the time complexity is order of log n. But the cost of the algorithm is governed by this recurrence relation. The cost on an instance of size n is twice the cost of the invocations on size n by 2 each. That is, we invoke the algorithm on the left side as well as the right side. The cost of both the invocations would count. So, we have a term 2 times C of n by 2. And then for combining them, we would require n by 2 processors on the right side to be active. All these processors will have to read the rightmost value on the left side and add this value to their own values. So, there are n by 2 processors operating for one step, which is a cost of order n. Therefore, the recurrence relation is C of n equals 2 times C of n by 2 plus C2 of n. This is the recurrence relation that is familiar to you. This is identical to the recurrence relation for merge sort. So, you know that the solution for this recurrence relation is order of n log n. So, the algorithm runs in order of n log n cost in order of log n time. As you can see, this is worse than the previous prefix sums algorithm that we have seen, and the way the algorithm is specified, Brent's scheduling principle will not apply directly. That is because the algorithm is a recursively specified one. But of course, it uses a very different algorithm design technique. It uses divide and conquer, whereas the previous prefix sums algorithm that we have seen was a balanced tree algorithm. Now, can we apply Brent's scheduling principle on this algorithm? On the face of it, it cannot be. But every recursive algorithm can be converted into an iterative algorithm. And if you convert this algorithm into an iterative one, you would find that Brent's scheduling principle would be applicable. And therefore, the cost of the algorithm can be reduced from order of n log n to order of n. That would be possible only on the iterative version of this algorithm. As another example of divide and conquer, we would design an optimal algorithm for finding the minimum of n numbers on common CRC-WPRAM. While ago we have seen an order double log n time algorithm for a cost of order of n times double log n. This is the second minimum algorithm we saw. Using n processes, that algorithm ran in order of double log n time. Let us say we want to convert this algorithm into an optimal algorithm. For doing this, what we do is this: given an array of size n, where we have only n by double log n processes, we divide this array into segments of size double log n each. The size of each segment is double log n. So, the number of segments would be n by double log n. And we assume we have n by double log n processors. That is, we have one processor per segment. So, we can assign one processor per segment. Using these processors sequentially, we can solve each segment. That is, the first processor will scan the elements in the first segment sequentially and find out the minimum and output the minimum. The second processor does the same in parallel and simultaneously, and so does every single processor. Since the size of the segment is double log n, this would take order of double log n time. So, this is an order of, since each segment is of a size double log n, with one processor per segment, the minimum within the segment can be found in order of double log n time. Now, to find the global minimum, all that we need to do is to find the minimum among these minima, among the local minima. So, we have n by double log n local minima. Now, the solution should be obvious to you. There are n by double log n local minima, the minimum of which is the answer that we seek, and we have n by double log n processors. So, to solve this problem, we can invoke the previous algorithm, that is the second minimum algorithm. So, this is our third minimum algorithm. So, to summarize, this algorithm proceeds in this fashion. This algorithm assumes n by double log n processors. It takes an array of size n, divides it into several segments of size double log n each. So, there are n by double log n segments. We depute one processor to each segment. The processor will solve the segment sequentially. Since the segment has a size of double log n, the sequential solution will take order of double log n time. So, out of each segment we pick out one minimum. Since there are n by double log n segments, we have a total of n by double log n local minima. The minimum among these local minima is the global minimum that we seek. But since we have n by double log n processors, we can solve this in order of double log n time. The number of processors identical to the number of elements we have. Therefore, this can be solved now in, strictly speaking, double log of n by double log n. This is the problem size now. So, when it is solved like this, since n by double log n is less than n, you can say this is order of double log n. So, invocation of minimum 2 will take order of double log n time. This is in addition to the time we spent within the segments. Within each segment, we spent order of double log n time. Since all the segments were solved in parallel, the total time taken is still order of double log n, and we have used only n by double log n processors. Therefore, this is an optimal algorithm. The cost of the algorithm is order n. And the model that we have used is common CRC-WPRAM. So, this is an optimal algorithm. You cannot be expecting to asymptotically improve on this. So, the problem of finding the minimum of n numbers on common CRC-WPRAM can be solved in order of double log n time for a cost of order n, which is optimal. Okay, that is it from the 7th lecture. Hope to see you in the next lecture. Thank you.